Hi, in this video, we want to take a look at interfacing the bnlearn package with parallel package in R. Okay, so for parallel programming, the idea is that our computer, our machine, has multiple cores that are able to do computations for us. And what we want to do, we want to get as many of those cores as possible involved in our project. So whenever I'm doing conditional probability models, those take a long time to learn. They take a long time to compute. All right, so if there's something I can do to speed up the process, that's highly advantageous for us. Now, whenever you do parallel programming, you run the risk of actually slowing down the system, believe it or not. And that comes from the fact that the cores have to communicate and coordinate together. And if you implement things poorly, you can actually slow down the entire process. Now, what we're going to do in this video, we're going to look at how the bnlearn package has built-in features to enable us to do parallel programming without us putting a whole lot of effort into it. And I did some benchmarking, and worst case scenario, we really don't have to worry about it being slower. That we really have nothing to lose and we truly have things to gain from just implementing parallel programming in the way that's already inherently built in for us. We can, in addition to these features that we inherently have, we can also use for each, and we can also use the cluster apply functions if we choose to use those to be able to do parallel programming. And my opinion is that in R, you generally want to either use for each if you have to have it in the form of a for loop, or use one of the cluster apply functions. All right, so this code is to a large extent copied and pasted from the bnlearn.com website, but in here I went through and I have similar examples. They are different examples, but I am pretty much following the structure. The text is almost the same. So if what I have is not enough for the examples, you can go to the website and find some more. There are some differences. All right, so the first thing that we need to be mindful of is that Bayesian networks are computationally intensive. Anytime we have conditional probability models, such as market basket analysis and Bayesian networks, they're going to be computationally intense. And so it is a huge advantage if we can pull in additional computational resources. A super important function for us is the make cluster function within the parallel package. What this function does, this goes and this says, hey, this resource, and this resource are available for computations. Something that's nice about much of the Bayesian network format is that we're doing a whole bunch of conditional independence tests. And if I have two nodes over here, and I have two completely different nodes over here, when we do conditional independence tests here, it doesn't influence the conditional independence of what's going on over here. Why is this important? To be able to do parallel programming easily, we need to be able to do things where the previous result or what I'm doing now does not depend on previous results, previous computations. If I'm working on a project and we're doing some computations where we need previous computations on the current computations to achieve our goal, then parallel programming gets a lot more difficult, and it may not be possible. If we attempt to use it, it may not actually speed up, it may slow things down. But because of the structure of Bayesian networks with the separate conditional independence tests, this is a good fit for parallel programming. All right, so let's go ahead and start looking at some code. So we're gonna pull in the bnlearn package. So remember that most of the time we wanna use the double colon notation to determine which package and which function we're using, but bnlearn doesn't fully support that schema, and so we need to fully attach bnlearn for us. We're going to be using the parallel package to make clusters and then tell how to use each cluster. And we're going to be using the alarm data set to make our models. Now, make cluster can make a wide variety of clusters, not wide variety, but multiple types of clusters. For us, we're really just going to be using the default cluster format, and that'll be enough. That won't change what's going on. Now, the default notation in R for clusters is CL. So I'm going to stick with that convention, is that CL is the output of the make clusters command. All right, so what I'm going to do, I'm going to make a bunch of models and I'm going to save them in a list. Something I've been noticing in the homework that we got last weekend was that students are kind of like letting all their objects like float around. It will improve your code if you start grouping similar items into lists. I know that lists are a very uncomfortable format to be working with if you're new to R, but it really is the right way to go. It'll make your workspace easier to keep clean, easier to figure out where things are, and you're able to iterate over lists. While if you have things floating around, it's much more difficult to iterate over such a process. You can still do it, but it's kind of difficult. Somewhere along the line, somebody told me to not use all of your cores when you're doing parallel programming. They didn't explain why, but I went ahead and just accepted it as being correct. And the detect cores function, what that does, that returns to me the number of cores available for computations. And I always divide by 2, because every time I've looked at a number of cores on a computer, it's been a power of 2, or divide by 2. And the max of 2 is just in case someone running my code just happened to have only 1 core on their machine, and then they do 1/2, and just to get it to work out. All right, so all of the constraint-based algorithms support support parallel programming very nicely, very easily. Really, if you look here, if I'm doing this algorithm, the fast IAMB algorithm, normally all we do is we just set what the data set is and we run it, and that's it. The only difference now is I'm saying, hey, I've got a cluster to work with. I just specify the cluster. That's it. That's all I have to do to change it up. And I'm going to get improved speed on my results. Improved speed with no disadvantage, why not? And so then we get down to grow shrink, same idea. Only thing we do is change the cluster is equal to CL. That's it. That's it. And we go through, and this example, I just ran through all of them. All right, so some things that we need to think about when we do parallel programming is that this step does require some use of time. All right, I mean, that's gonna be part of it. And the stop cluster command is also going to take up some time, but also there's a communications aspect between the clusters as they complete as they individually complete their tasks. And depending on how things are set up, that can actually slow us down. Usually it's not a big issue, but it's something to always be concerned about. You should always benchmark your processes before you start doing any heavy parallel programming, because potentially you could screw it up. Now, we also want to always stop a cluster after we're done. It's good practice. We don't want resources on our machine to be dedicated for something that we're not using. So stop cluster tells the computer, hey, free it up so I can use it again later. Now for parallel parameter learning, it's embarrassingly easy because what we do, we just take each node, we take each arc going into the node, and we fit it. And that's it. The parameter is so nice. And so because of that, because working on one node at a time is, I take a node and everything that goes into that node, I go over here with a different node and I take everything that points into that node on our network. Well, I can grab that data completely separate, and I don't need communication between the fitting. And because I don't need communication between fitting, this is an embarrassingly parallel process. So that's super easy to do for parallel programming if we choose to. And it's a good idea. Now, something about fitting the model when I use bnfit, I need to have directed arcs throughout. I know that some of us had problems with this for the homework over the weekend. What we need to do, we need to use either the set arc function or the choose direction function. And so what we're doing here is I'm attempting to set an arc in each direction. If I set arc, you'll notice I go to from, and here I go from to, and I set arc twice. And I just, I'm using a try statement to get that. So if there's an error, it'll be okay. Why is this important? All right, well, remember that in the bnlearn package, it does not want cycles. It does not want cyclic graphs. So if set arc here, if this would generate a cycle in my graph, bnlearn's not gonna let it happen. And so if this fails, I go ahead and I try to do it this way. And if I can't, and if it is possible to have a situation where neither one can be set to a direction without creating a cycle, but that's pretty rare, especially with the models built with these algorithms. So I'm not going to worry about it. Now, it would have been better for me to use the choose direction function after this to make sure that I have the best direction possible. But usually it takes a little bit of time, and I just wanted to get this lecture out, so I skipped it. And so here are the models after. So here's the model after I've set it up so that there are no undirected arcs. Every single arc is directed. And we can see that here. 34 arcs and 34 directed arcs. $19 arcs and 19 directed arcs. And so I mean, we can just look through, and it's all here. Just wanted to show you what we got. All right, so now, let me see, make sure I'm at the end. Yes, yeah, that's the end of it. I put them in alphabetical order so it's easier to know when I'm at the end. Now we actually want to fit it. So to be able to use bn.fit, what I have to do, I have to have a completely directed graph, which means I had to go through and use the set.arc function every single time. No problem, easy peasy lemon squeezy. And once again, I'm going to store the results in a list because that keeps everything nice and clean, easy to work with. I'm going to make cluster after I detect the number of nodes. And I'm just going to run through, and I'm going to run bnfit for each of the models that were just listed. So this list underscore models is my collection of directed graphs. I'm going to take the data, and I'm going to take the cluster, and I'm going to fit the parameters of the model. So how this actually ends up working is that for each combination of predictor variables pointed into a node, I get a table of the probability of values for the target variable. And when I'm all done, I'm going to go ahead and stop the cluster. Now, when I'm all done, I have a whole bunch of different models, one corresponding to each of the models we looked at previously. Here, I'm only going to look at the grow shrink version of it. just because I had fewer arcs than the others, and I want to keep it kind of clean. All right, so here is the conditional probability matrix for CVP. Here's the conditional probability matrix for PCWP. So this tells me if I know what LW is, I know the distribution of CVP, or the model distribution, that is. And the alarm data set is completely discrete. I will get something similar if I go through and do this with continuous data, with numeric data. The main difference is that it's going to be doing Gaussian regression. And there's plenty of output, plenty of tables, lots of tables. All right, so the next thing we want to talk about is to do parallel cross-validation. So what's going on is I have a whole bunch of, I've got different folds. And if I think about it, I can organize the folds and have each node perform a different fold task. So let's say the first node uses the first fold as the validation set and the other folds as the training set. And then the second node uses the second fold as the validation set and the others as the training set. And I can keep on going through. And that's how we can divvy this up so that all the cores can simultaneously perform all of our computations for us. And if I look at this, I do bn.cv. And the main difference from what we've looked at before is that I declare what the cluster is. Now, the help documentation in the bnlearn PDF says that for the bn, we can use a Bayesian model of class bn from the bnlearn package. I had a really hard time getting that to run. Sometimes it would work, sometimes it wouldn't for different models. I think what I need to do is build it in a different manner and then run it. But there were several times where I was just unable to get it to go. And remember to stop your cluster when you're done. Oh, and we can also do the BMDAS cross-validation. We can do that for holdout and custom folds also. Here in this format, I'm letting the machine choose the folds for me. Give me a little bit less to do. Now, we can do Bootstrap. So if I want a particular statistic from my model, and I want to know what's the distribution of that statistic, what I can do, I can sample my data with replacement, run the algorithm, get the statistic, sample my data again with replacement, rebuild the model, get the statistic, sample with replacement again, and then rebuild the model, get the statistic. I can do this a bunch of times. So I could do this like 10,000 times if I wanted to. Usually at work, I do about 10,000 for Bootstrap. And then I have a distribution of what the statistic is. And so I have a better intuition on what's going on. Here, I believe the default is only 200, which is rather low. But if I am doing something that takes a longer time to compute, 200 might be fine and dandy with me, because if it takes a long time, 200 might be the most time that I can commit to it. All right, so here we're taking a look at the Bayesian information criterion. Oh, something I need to say. When I said sample with replacement, I take a sample of the size of the data I have. So if I have 1,000 rows of data, I sample with replacement 1,000 rows of data. And so some rows are going to be left out, some rows are going to be in there multiple times. And by running through this, I get a reasonable idea of what the distribution of the statistic of interest truly is. All right, so here I go through and we get the Bayesian information criterion using the hill climber algorithm. And let's look at the histogram. And so it's kind of choppy, which kind of jumps out at me. Seeing like this weird pattern over here, this tells me that if I wanted full information, I wanted to be more complete about this, I would have to complete the number. I would have to greatly increase the number of iterations before I could really trust this. This looks kind of weird. This is unusual. So I would want to spend some time getting a better representation. The next thing we can take a look at is estimating the strength of our arcs. And we do this with the boot.strength function. There's also an arc.strength in the bnlearn, and that's my experience, that's a faster way to go, but it tends to, it will only give you the strength of arcs that are actually in your model. If you want a more comprehensive representation of the strength of potential arcs that you may or may not have in your model, then boot.strength is a good way to go. Now this part of the code, what this is doing is after I get the strength of each arc, I'm just sorting everything so that it's a little bit easier to interpret. So we're using boot.strength. I'm passing data and algorithm, just like I did before. The only difference is that I'm declaring the cluster that I'm using. And I've got it set up so that the estimates for strength and direction that are the largest are at the top, and the ones that have the weakest strength and direction estimates are at the bottom. And boot.strength gives us numbers from 0 to 1. We can also do queries using parallel computation. So if I do CP query, everything is just like it's been before. Now notice that CP query has this kind of weird notation for the event and evidence. So the event is, this is the probability I want to know. The evidence is the conditional values. So I want the probability of A given B. And that's what this will estimate for me. And we can see that the conditional probability of A given B is about 0.16. Now, if I want to use my Bayesian network to do, to randomly generate observations, then we can use the CPDist function. So what this does is I say, hey, here is the conditional values. I want you to go through and I want you to do random value generation on those nodes. And it's pairwise on those nodes. So if these are not independent of each other, I want the distribution of my randomly generated values to reflect that non-independence. Let's take a look at the output. And here I told it to just take the head, the first 6. Here are the values we get. So it looks like normal is going to be more common for each of these whenever we know that HIST is true and TPR is high. All right, that's all I've got for you. I hope you're doing well and staying safe with this coronavirus. Take care and goodbye.